Welcome to the nuclear chemistry simulation. In this simulation, you will learn all about the atomic nucleus, the energies and processes that occur within, and how one atom of an element can turn into another. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch to play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you've played a Labster simulation? Perfect. Then let's get started with your first mission. Have you ever wondered what the atomic nucleus is? Why are some elements radioactive? Or even what is radioactivity? Congratulations then! At the end of the simulation you will be able to answer all of those questions. Let's start. Have a look at the big screen in the middle of the lab and click on it. This is an atom. It is the smallest particle of a chemical element that can exist. It is formed from electrons which orbit protons and neutrons in a nucleus. Click on the screen to keep learning. Protons and neutrons form the nucleus and they both have approximately the same mass. Protons are positively charged whereas neutrons have no charge at all. Click on the screen one last time. Electrons orbit around the nucleus. They are negatively charged and their mass is 1,835 times smaller than a proton or neutron. During this simulation we will mainly focus on the particles in the nucleus. They are called nucleons, and as you just heard, there are two types, protons and neutrons. Move to the hollow floor to analyze the nucleus. Have you ever wondered what keeps protons and neutrons together in the nucleus? After all, there are several protons, all positively charged, and equal charges repel each other, right? Let's try and figure this out. Place two protons on the hollow floor and press play. See what happened there? That's the effect of the electromagnetic force. Two equal charges repel each other. But what happens if we push them closer together? Place the two protons closer to each other and press play. Did you see that? They stay together for some time. This is caused by the strong nuclear force, which pulls particles together. This force is only significant at very small distances, so we need to place the particles close enough together for it to act. This force affects all particles that are close enough to each other, and it counteracts the effect of the electromagnetic force. The distance that this force acts at is so small that this interaction only occurs inside the nucleus. If the strong nuclear force affects all particles that are very close to each other, what will happen if we add two neutrons to our nucleus with two protons? No. This is incorrect. Please try. No. This is incorrect. Please try again. No. This. No. This. Exactly. Since neutrons have no charge, they do not have an effect on the electromagnetic force. However, they are particles within the nucleus, so adding them will increase the strong nuclear force in the nucleus. Let's go and test this out. Place two neutrons and two protons, then press play to see what happens. They're all packed tightly together. This is essentially the nucleus of an atom of helium. The neutrons increase the strong nuclear force without influencing the electromagnetic force, and this makes the nucleus more stable. Why did the nucleus stay together when we added 2 neutrons? No. This is incorrect. Please try again. Correct. Neutrons increase the strong nuclear force without influencing the electromagnetic force, so this results in a more stable nucleus that stays together. Interesting. If we add more neutrons to our helium atom, the element doesn't change. It is still helium, since the element depends on the number of protons in the nucleus. However, the molecular weight does change. It is a heavier version of helium. These heavier or lighter versions of an element, caused by the change in the number of neutrons, are called isotopes. What would happen if we add another neutron to our nucleus? Add another neutron to the helium nucleus, but don't press play yet. You just created an isotope of helium. This is called helium-5, since it has 2 protons and 3 neutrons, which gives a total of 5 nucleons. Now, let's press play on to see what happens. Press play to see how the new nucleus behaves. Did you see what happened? One of the neutrons was pushed out of the nucleus and we have helium-4 again. This happened because helium-5 is very unstable. There are only certain combinations of protons and neutrons that are stable in the nucleus. Those stable combinations are called stable isotopes. The rest of the isotopes are not stable, and they are called unstable isotopes, or radioactive isotopes. Radioactive isotopes, since they are unstable, tend to decay into other isotopes that are more stable, or even other elements. Yes, you heard correctly, one element can turn into another. Different radioactive isotopes have different probabilities of decaying into other isotopes or elements. There is no way to know when a specific atom will decay, but we use a concept called half-life to estimate it. Half-life is the time that it will take for half of the atoms of a certain mass of a radioactive isotope to decay. Oxygen has an atomic number of 12. However, the isotope oxygen-14 has a half-life of 70.62 seconds. What would happen to 1 gram of oxygen-14 after 70.62 seconds? Yes. A half-life of 70.62 seconds means that half of the atoms of the element will decay in that period of time. This means that half of the 1 gram of oxygen-14 would have decayed after that time. Some isotopes have half-lives of a tiny fraction of a second, while others have a half-life of billions of years. There are 3 different ways by which a radioactive isotope can decay into another isotope or element. They are called alpha, beta and gamma decay. Radioactive decay occurs as the isotope is searching for a more stable composition for the nucleus, which sometimes implies less stable intermediate steps. A more stable composition means lower energetic level, but since energy is always conserved, if the atom decays and lowers its energy level, some energy needs to be emitted. This occurs in the form of alpha, beta, and gamma radiation. This is the basic principle of nuclear energy, but we won't cover that in the simulation. Click on the alpha decay button on the floating screen to your left to start analyzing alpha decay. Uranium-238 is the most abundant isotope of uranium. More than 99% of the uranium in the Earth's crust is uranium-238. It contains 92 protons and 146 neutrons. Uranium-238 is not stable though. It is unstable and therefore radioactive. In this case, it undergoes alpha decay. Press play to see how alpha decay occurs. In alpha decay, 2 protons and 2 neutrons are expelled from the uranium-238 nucleus. This results in a nucleus with 90 protons and 144 neutrons. Since the number of protons has changed, We now have thorium-234 instead of uranium-238. Note that you can find a summary of alpha decay on the big screen in the middle of the lab. These 2 protons and 2 neutrons are essentially a nucleus of helium, as you might remember. This free nucleus of helium, without electrons, is called alpha particle, hence the name alpha decay. The total loss of mass is 2 protons and 2 neutrons. What happens to the atomic number during alpha decay? Precisely. Since 2 protons are always expelled from the nucleus, the resulting nucleus will always have a lower atomic number than the original nucleus. Click on the beta decay button on the floating screen. When uranium-238 loses 2 protons and 2 neutrons, it turns into thorium-234, as we saw previously. However, it is still not stable. Press play to see how beta decay occurs. One neutron turns into a proton and highly energetic electron. The highly energetic electron is then expelled out of the nucleus. This particle is called a beta particle, hence the name of the decay. The total loss of mass is 1 electron. Additionally, 1 neutron was turned into a proton. This means that the atomic number is now 91 instead of 90. This results in protactinium-234M. The M indicates that it is in a high energy state. Note that you have a summary of beta decay on the big screen in the middle of the lab. How big is the loss of mass of the nucleus in beta decay? That's right. In beta decay, the loss of mass is 1 electron, and since electrons are way less massive than protons and neutrons, the loss of mass of a nucleus undergoing beta decay is smaller than in alpha decay. Click on the gamma decay button on the floating screen. Protactinium-234M is a high-energy state of protactinium-234. Sometimes, after alpha or beta decay occurs, the nucleus can be in a high-energy state and can be rearranged to reach a lower energy level. Press play to see how gamma decay occurs. When protactinium-234M is created, it tends to decay to a lower energetic level. When it does reach a lower energy level, since energy is conserved, the nucleus emits an extremely energetic photon and protactinium-234M turns into protactinium-234. This highly energetic photon is called a gamma ray. Photons have an extremely low mass, so there isn't any noticeable loss of mass in the nucleus. Note that you have a summary of gamma decay on the big screen in the middle of the lab. Why is there almost no loss of mass in a nucleus undergoing gamma decay? Bingo! The only change in mass that happens is that a photon is expelled from the nucleus. Photons have an extremely low mass, so the change is almost imperceptible. Well, seems like you have mastered the 3 different types of radioactive decay. Feel free to repeat the different animations on the holo floor by pressing the buttons on the floating screen and play on the holo floor. Additionally, since we are in a virtual lab and everything is possible, let's do a little experiment that would be very complicated to do in real life. Once you are finished looking at the different types of decay, go to the workbench on the other side of the lab. Here you have 1 kilograms of 3 different isotopes of uranium. Each isotope goes through a different type of decay, 1 alpha, 1 gamma and 1 beta. Do you think that we can identify which element is experiencing alpha, beta and gamma decay by using this scale? Correct. The different types of decay involve different processes and particles, so the loss in mass depends on the type of decay. Place each of the uranium isotopes on a scale. Note that you can find more information about the isotopes if you hover over them. We have an exact weight of 1,000 grams for each of the isotopes. Oh, one small detail, I forgot to mention that some of those isotopes are very radioactive. Luckily we are in a virtual simulation. In real life you won't even be able to be anywhere near these isotopes without being exposed to high levels of radioactivity. The half-life of those 3 isotopes is different. So, in order to be able to compare them, we will check the weight of each of them by letting a time equivalent to each's half-life pass. So, firstly we will sample the uranium-228 after 9 minutes, then the uranium-239 after 23 minutes and lastly the uranium-235M after 26 minutes. By doing this, all isotopes will have gone through a time equal to their half-life. Press the time travel button to speed up time to 9 minutes in the future. Okay, it seems like the weight of uranium-228 is 991.250 grams after 9 minutes. Press the time travel button to speed up time until 23 minutes in the future. Okay, after 23 minutes have passed, the mass of uranium-239 is 999.999 grams. No worries, you don't need to remember all those numbers. Press the time travel button to speed up time until 26 minutes in the future. Okay, a total of 26 minutes have passed, and the weight of the uranium-235M is still 1000.000 grams. Seems like we have all the information we need now. Now it's time to identify our elements and their decay. Here are listed the final weights of the 3 isotopes after a time equal to their half-life have passed. 1. Uranium-228 equals 991.250 grams. 2. Uranium-235M equals 1000.000 grams. 3. Uranium-239 equals 999.999 grams. What type of decay is each of the isotopes undergoing? That's right. Alpha decay causes the loss of 2 protons and 2 neutrons from the nucleus, while beta decay only causes the loss of an electron, and gamma decay of a photon. This means that the isotope that lost the most mass should be the one going through alpha decay, and the one with no reduction in its mass should be the one going through gamma decay. As a bonus, I guess that you have heard about carbon-14 dating. Well, carbon-14 is a radioactive isotope of carbon with a half-life of 5,400 years. If we find a tree fossil, for example, we can measure the amount of carbon-14 in it and estimate the age of that fossil. We can infer the initial concentration of carbon-14 in a fossil by using the atmospheric concentration of carbon-14 at that time. How can knowing the half-life of carbon-14, its initial concentration and measuring its concentration at the moment of the discovery allow us to estimate the age of the fossil? Exactly. We know the initial and final concentration of carbon-14 in the fossil, and the half-life of the isotope gives us the rate at which it decays, so we can estimate the age of the fossil based on this information. Isn't it amazing? Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now. Press exit to close the simulation. This will open a survey. Please take 1 minute to provide your feedback. It will help us to improve Labster. I gain relevant knowledge by using the simulation. I found this simulation motivating. I feel more confident about. I feel that I can apply what I have learned in the simulation to real-world cases.